Hello, hi Nick, how are you?
I'm doing all right. How are you?
I'm sorry, I'm late a little bit. So, any question? Any questions so far?
I'm not really too sure yet.
Okay. Yeah, I'm sorry. Actually, I talked to a student in this class, in the same class regarding the recommendation later, but his attitude is totally wrong. So I spent some time to actually talk to him. Sorry for that. Okay, I'm happy to write recommendation data for any student that I teach. Okay, but I do need to know about student. I just asked for some personal information like resume or spreadsheet, but he refused to give me any information. Just want me to write recommendation later, and I told him that that's impossible. If I don't know about a person, how can I recommend him? Right? There's no way. And he got mad, and I don't know. I'm As a professor, I don't earn money by writing any recommendation letter for anybody. So there's no, it's not for my personal benefit. It's for students' benefit. So I don't know why this person had to be mad. I don't know. It's for his benefit, not for me. I don't need a recommendation letter, right? Why should I need to have a recommendation letter? I don't need that. And as a professor, I'd have no obligation to write any recommendation later for anybody if I don't like, right? And I only write letters for people who actually has good personality and actually is working hard, right? So I need to know somebody. Usually I don't have such problem, right? I actually, most of the students ask for it, I'll try to help them. But just a little bit of the information will help me to know better about you and being able to recommend you in the right way. Okay. So that's my policy. Still want student. If there are some students who want to actually have my recommendation for application of graduate school or applying for job, I'm still happy to do that. But you need to let me know who you are and what's the main reason or your main strengths that I need to emphasize on. Okay. Anyway. Okay, so this is the last week for this course. We actually go into the very last part that actually is a mobile robot. And mobile robot is the vehicle part. As I say, a robot has two major systems. One is the manipulator system. So you do have a robot arm, right, to pick up something, and you do have the tractor or wheel or leg. That is a vehicle part. So both the robot arm part and the vehicle part, both of them has a feedback loop. And you may have a vision unit or audio unit or ultrasonic unit to sense the environment. Once you sense the environment, you need to build a 3D model for your environment. So where you are and what is the obstacle and how should you move your arm to reach it or you want to give up. Okay, that's actually a system that actually would be helping. Okay, you how you actually not manipulate your system. So the mobile robot, in a way, is actually talking about the vehicle part. So the vehicle part is the wheel. Sometimes the wheel, sometimes it's leg, sometimes it's a rocket. Uh, the propeller system, whatever system it is, just help the robot to move its body from point A to point B. Okay, that's the mobile robot. And same thing, you will have the sensor portion to sense the environment and need to build up the 3D model of the environment and put back to the whole system to try to sense it. Okay. go back to the whole system. So in a way, it's similar to the computer graphic, because your image that you take from the environment will be feedback to your computing model. And the computing model is your understanding of the environment. Okay, so here you need to move your vehicle, say maybe bicycle, maybe unicycle, to move along the path and then to avoid some obstacle, something like that. Okay, so you need to build a model for it. Okay, so mobile robot. So fundamental problem of mobile robot is a locality where the robot is. Okay, and the path and the trajectory planning. Okay, and motion control. How much power need to apply to the motor, the torque, the force. Okay, how fast should I move my wheels? Okay, so to be able to solve these problems simultaneously in an environment in which are uncertain. Uncertain means that you may be in a battlefield. So your environment at the 1 second is this way, but the second, the whole environment may be being bombed. So the environment may change in a second. So let's consider that, for example, you do have a robot combat system in the Ukraine area, right? And it's actually a autopilot cars. Okay, autopilot tank, and the environment actually keep changing because suddenly there will be some change in the landscape. Suddenly there may be your enemy is moving, okay, and there may be some obstacle just drop. Okay, so the environment is dynamic, and your visibility may drop because they may give you some sort of smoke. Okay, to block your vision or to block your ultrasonic sensor. Okay, so basically you need to take care all of the sensors information and try to come out with the best estimation of the environment and make the right move. Okay, make the right move. So basically, perception is very important. Perception is the robot position, orientation, and the velocity. Okay, proprioceptive. Okay, and then you need to know about the exteroceptive, that's the relative position of obstacle and other robot. Okay, you need to know about where you are, and you also need to know about where the other people or robot are. Okay, and you can use so these are actually trying to build up your environment using modeling, using your sensor, using your information, using the GPS, okay, using the rangefinder, using camera, using textile sensor or proximity sensors, okay, and build up your system, your model for the environment, and then you basically operate your robot in that environment. Okay, so they are reactive architecture, do not think. Okay, it actually reactive means that you do not have planning, you just sense the data and react, That's actually is the reactive architecture. They are hybrid architecture that actually do have sense, planning, and react system, and also reactive system. That's hybrid. And there's another one that's actually purely behavioral architecture. So behavioral architecture is somewhat like an event-driven type of architecture. So there are many event-driven handler that you can have, and then once event happen, you drive something. So event-driven, say for example, you have the counter or anti-missile combat system. So there's a missile coming in, closing into a certain range, then you fire your anti-missile to try to shoot it down. Okay, that's actually behavioral architecture. That's driven by the automatic detection. Okay, that's behavioral architecture. So here you can have the hybrid system that you do have a localization. Okay, you have perception, and your physical robot will sense the environment and take image or ultrasonic sensor to sense the environment and build up your local map, the model you have, okay, and then try to actually compare with your mission, your planning, path and create a path or trajectory planning, and then control your robot movement to achieve the goal. Okay, so that's like that. And here we do have some math. This portion I would actually just bypass it. It's too much. Okay, and you do have a disk rolling on the plane, and there's a controllable called CEDA, and you can control that you're rolling into achieve it. Okay, and okay, these are more complicated math. We actually try not to go into the detail. Okay, and unit circle. Unit circle is only one wheel that actually is controllable unit. The other two wheels, they may be moving, but they actually have no control of the theta, and they are not driving. So this is one wheel, self-driving robot vehicle. And you can have a synchronized driver. If the three wheels, you actually coordinate the wheel motion at the same time. Okay, and you may have a bicycle that actually have two wheels, and you can control them. Okay, and there are some mathematical model. And tricycle, okay, tricycle, three wheel, four wheels system. So your front drive car or back drive car is something like this. Okay. Okay, this formula, I try not to go into those details. It's too much. Okay, too much. It actually take a long time to understand it. Okay, so here we basically roughly go through this whole chapter. The key point for this chapter is we try to sense the environment and actually try to sense the environment and then move your vehicle to the right location. Okay. And then let me go back to here. Last time we do low level control. And then let's look at the robot control. Okay, so robot control, we do not talk about low level control. That actually is a feedback loop. Okay, and there's a PID controller, and high level controller is a finite state machine or microprocessor. Okay, so in a way, you actually will program your robot try to control your feedback loop and also your robot motion. Okay, so that's the architecture we do have. So robot architecture is similar to computer architecture. Okay, computer architecture is the architecture for personal computer, and robot architecture is the architecture for the robot. So in a way, robot architecture is also an extension of computer architecture. Okay, so it's also an extension of computer architecture. So your computer architecture comes with an operation system operating on your instruction set. Okay, so same thing, this whole set for robot, you also have that. Okay, so you can build your robot using ASIC, application-specific integrated circuit, or you can build a microprocessor using the robot OS. ROS is robot OS. Okay, using robot OS to build a robot. Okay, and there are block diagrams for such a robot, including the wheel drivers, locator T, okay, navigation. Okay, these are complicated system block diagram. And you design a robot, including the sensor, including the controller, including the camera, including the display, including the bumper control. Okay, laser range finders. Okay, your control has the hierarchical control. There's a sense, plan, and act. Okay, you have the relative reactive control. Reactive is you sense and react, sense and react. Someone hit you, you counterattack. Someone hit you, you counterattack. That's reactive. Okay, and then traditional is the sense. You do planning, how far the enemy is, and then take action. That's a hierarchical way. Okay, and third one is behavioral based. Behavior based is the event-driven one. You sense, planning, and act, but you will choose the right one to act. So it's somewhat like you choose the right event handler to run your robot operations, okay? And you can also design it so that it's a hybrid. Hybrid means that you are partly deliberative, partly with planning, partly just reactive. Okay, reactive control is faster because you sense and you react. It actually is faster. And the hierarchical or behavioral based, it takes longer time because you need to use computer to do planning. So hybrid one actually is combined the two. Sometimes use the directly sensing and react. Sometimes you actually add the planning into it. Okay. So this one is actually a different one. But nowadays, because of the AI, so the planning become not just using the algorithmic method, but maybe also using the AI approach, machine learning approach. Okay, so this portion, because of the advancement of the microprocessor, so the performance of such architecture is more robust than before. Okay, so these are different categories of the control: deliberative control, reactive control, hybrid control, and behavior-based control. Okay, so you have sense, plan, and action. This is deliberative paradigm. So sense the world, and then update the world model, okay, and then generate plan. This one is typically the deliberative paradigm. The problem is the planning would be the bottleneck. It is a computer. It is a computer, okay? It is a computer, so it is a microprocessor, a computer, so it takes longer time. If your planning take too long, and this planning may also involve AI, so actually it depends on how the decision quality and how much time or latency you can tolerate. Okay, reactive is that you do not do planning; it just sense counterattack. Okay, so it's faster, but the problem is that the decision is very poor sometimes because you do not think about it. Okay. So these two, in terms of processes speed, reactive is faster. In terms of the decision quality, deliberative is better. Okay. Okay, and the behavioral based architecture is that okay. That's actually have the planning, but we can have multiple processors to do it in parallel, and take different events in different way. Okay, and have an event-driven way of doing it, and then we have an arbitration. The arbitration will decide that what should I do. So as a robot, you can push the door or go through the door or approach object or follow a wall. So these are four different plans. So you can consider these are four different events that you may be calculating. And the arbitration will pick one. Okay, pick one for your robot to see which one you will use. Okay, so behaviors are the basic building block for robotic actions. So you can consider that these behaviors are the functions, the methods, the basic events handler for a robot. Okay, and behaviors support good software design principle to the modularity. Okay, so you can every time update one of the behavior and update your robot operations. Okay. So here you do have an arbitration. So different behavior-based architecture have different approach to provide arbitration. Okay. So hybrid paradigm, world model used for planning, closed loop reactive control. Many architecture of today follow such a paradigm. Choice of robot control architecture. Okay. In many cases, it is impossible to tell just by observing a robot's behavior what control architecture it is using. Okay, so here it's very hard to know what architecture it is, but in design you need to know which one you will use based on your requirement. In terms of latency, you can tolerate. In terms of processor you would like to use. In terms of the difficulty of the task Okay, so for example, like if we do look at the iRobot, so that's actually if we actually look at the so-called iRobot, let's look at the vacuum cleaner called iRobot. So let's assume that here we actually have a try to okay, let's try to actually think about it as iRobot scenario. Okay, so iRobot actually it is a vacuum cleaner. So you do have a room, and there may be a door. There may be a door you can open, and then there's a door, right? And there may be a sofa, a set of sofa. There's a table. Okay, right here there may be a kitchen and a refrigerator. Okay, and there may be an island. Okay, whatever something like this. So your iRobot is put over here and start to do scanning, start to do cleaning. Or for some angle, you actually cannot go there, so you actually will sense whatever environment is. So iRobot will sense the environment and build up such a map. So where there are obstacles, you will actually use the iRobot's scanning and then build up the so-called environment. And this environment, two-dimensional diagram is good enough. You do not need to have 3D because your iRobot will not move up vertically or move down vertically. You will not. And once there's an obstacle on the side, then your iRobot can never go through it, right? Your iRobot can never go through it. So basically, these are the sensing of the environment. And iRobot just need to go to forward, follow the wall, approaching, okay? And iRobot do not have the open the door option because it is not a real robot. So there's no robot arm to open any door. Okay, there's no something like that. So you actually just need to go left, right, up, down, and something like that, and sense the environment and build up your two-dimensional graph for it. Okay, so that's actually is the architectural requirement for the iRobot. Now, based on that requirement, you have to think about what control strategy is the best for your iRobot. Okay, so what kind of processor I need to have, what kind of sensor I need to have. So here, because you really do not need to have a sensor of color image. No, you don't. Because the environment, the color is yellow or red or black, it doesn't matter. So monochrome camera is good enough, okay? But it do need to be able to sense whether this is a obstacle. Can you pass vertically or not? Okay, that actually is the key element you need to have. So you may use the ultrasonic sensor to see how far the obstacle is. And also you may use a black and white image to build up the map, okay? And you may use a microprocessor to control the movement, okay? And it's an iRobot, you might have in actually a disk-like operation. So you may have an iRobot, you may have two wheels and they maybe only one steerer. So tricycle with one steering wheel may be good enough, right? It's good enough to drive into the different direction, okay? Or if you want to use the three synchronized disk to make a rotation, that actually is also okay. So basically, these are something you need to figure out what kind of the wheel you will need to have, and then also find the right processor for it. Okay. And now you need to find a operation system that can actually handle it. So there is one consortium called Robot Operation System, Robot OS. So there's a consortium called Robot OS. Okay. And this Robot OS is a robot one OS that can be used to develop different robots. Okay, you can also use Linux whatever system. Okay, this robot OS is one OS. Linux system is also another OS, and these are okay to drive the your processors. Okay, to drive your processors. Okay, so some criteria for selecting architecture. So you need to actually make your decision based on the parallelism, hardware targetability, runtime flexibility, and modularity. Okay. And then targetability, robust, ease of use, and performance. Okay, based on these different criteria to choose the right control architecture. And usually it's a response time, environmental mode, model, internal states. Okay. And look into different category to make the decision. Okay, so these are some more detail in the design. Okay, and they are something you need to build. Okay, something you need to build. The last comment is like, okay, the planning portion you may be a microprocessor, but you can also use a reinforcement learning to learn your past parameters and then update your system. Okay, so you can also bring in machine learning and the big data into your robot system. Okay. Okay, that's it for today. Any questions so far? I kind of go through the robot control for mobile robots. Any question?
I don't think so.
That's the last chapter, okay? What's any other question about this course so far? How are you so far in this course?
I think I'm a little bit behind right now, but I've been working pretty hard on stuff. I got a few assignments I'm going to turn in tonight, and I've been working on the final as well.
Yeah, okay. Okay, so Friday I will still have a course, okay? Friday I still would have a course. So let me know if you have some question there. And in between, if you still have some question you want to ask, still going through email or going through the Facebook will be faster, okay?
Okay, thank you.
Okay, if no question, that's it for today, okay?
Okay,
See you next time. See you. Bye-bye.
bye.